that a chiral object is an object in which its mirror image cannot be superimposed onto the object. And this is clearly visualized when we have our hands, so left and right hand mirror image of each other, but we cannot superimpose it. And this has profound physical implications beyond just the geometry. For example, enantiometers smell different, or they rotate the plane of polarization of an electromagnetic wave in opposite direction. The microscopic explanation of the optical rotation is basically electromagnetic coupling. So that means that the magnetic field induces an electric dipole, and by reciprocity, the magnetic field induces an electric dipole. Did I say it right? Yeah, so this is not valid for non-zero frequency, and we can expect some kind of electromagnetic coupling at zero frequency. So I just want you to imagine this device. We have graphene, and we put a patch of graphene on top of that monolayer, and we can change the orientation. That's a twisted graphene molecule. And now imagine a mirror plane here, and we have the mirror image. And what happened? We have that the mirror image of that molecule is the patch with a negative twist. So in principle, we have a chiral object. So in chirality, we can have what is called false chirality or true chirality. So do we have a true chirality or a false chirality? And we are going to test that at zero frequency. So basically, we are going to put contacts to the left and to the right and inject a current with a bias. So we have an electric field. So what do we expect in the case of a true chirality device? The electric field will induce a magnetic dipole in our system. And that's the idea that we have. Well, probably you can guess the answer is yes. We have a chiral response. So today I'm going to just to explain the step that we took to find that answer. First, we have to characterize from the point of view of transport our molecule. Since we are after the magnetic response, we have to look for the current, the total current, and the local current distribution, because we are looking for current loops that produce the magnetic moment. Then we try to explain this response in a more general language. And finally, well, I will reach to the end and I will summarize our results. So this is an image of our system. So we have a square region with a side length of 50 nanometers. This is the monolayer. When we contacted the monolayer, these black dots here means that we have the contact. And we have a top patch that we can change the angle with a 40 nanometers side length. And we can change the twist angle following this equation that is used for infinite twisted bilayer graphene for commensurate angles. So first, to solve this problem, we have more than 150,000 atoms. And we have to go beyond the nearest neighbor approximation to reproduce the properties of the twisted bilayer. So that puts a stress on our calculation, because we are going to study the transport properties, specifically the conductance, and we cannot use the recursive technique. So we have some problem, and we have to represent the Hamiltonian in a sparse matrix representation. And to avoid the momentum mismatch between the contacts and the device, we use an effective contact. You know, traditionally, the self-energies of the contact are calculated recursively, but as you know, we have more than 50 neighbors. Using this approximation, we select neighbors between a radius of 4 times this carbon-carbon distance. So an atom in the middle has more than 50 neighbors. So we cannot use that, and we will have a large momentum mismatch. So we decide to use an effective model that basically depends on the density of states of the contact and the coupling between the contact and the device. For graphene, we reach to this answer, where T is basically the nearest neighbor hopping. Well, first we have to check if we are reproducing what is expected for a twisted bilayer graphene device. That is, the shifting of the Van Hoff singularities, and for low twist angle, a high density of states. And you can see here the plot of the density of state for different twist angles. And you can see that the Van Hoff singularities are moving toward the charge neutrality point. That is not zero because of the self-doping, because we have to include more than nearest neighbors. And when we plot the local density of a state for this peak, we found that the wave function of the electrons are localizing on the AA stacked regions. So we have nice behavior between the monolayer and the bilayer. We have some AA regions, and you can see here that because of the edges, they are not developing the high density of a state. We also put hydrogen on these zigzag edges to avoid complications to interpret our results, because to avoid the zigzag edge states, and we start working with an armchair nanoribbon. So in principle, now we are confident that we can calculate the properties of this molecule. And this is the first calculation, the conductance, when we identify three regimes. The first regime, the weak coupling regime for large twist angle. So that means that the top patch is completely transparent. And you can see with the green line here, basically the conductance of the nanoribbon. You can see a nice defined quantization plateau here, but you can see that we cannot see the plateau zonally defined, but this is an effect of the effective contacts, because we have a Fabry-Perot oscillation, but it follows the conductance of the system. When we reduce the twist angle, we reach the intermediate couple regime between 2 and 10 degrees. So you can see that the width of the plateau is reduced, and appears some peaks superimposed to the plateaus. This is basically because the patch is not so transparent, so they are scattering electrons and creating some evanescent states, and they appear as a new channel to conduction. And finally, the strong coupling regime for low twist angle, when you see that the conductance quantization is completely gone. You can see rapid oscillation, and that's explained because we have a large density of state with the same energy. So the electrons in the nanoribbon are scattered to a large number of states with the same energy, and this appears as interference. So we are confident that we are reproducing the properties of what is expected for twisted bilayer graphene. So we then proceed to calculate the current. And we initially calculate the total current applying a bias between the left and right contact. And you can see how it evolves with changing the twist angle. And surprisingly, you can see that also for low twist angle, it oscillates. It had similar values with the completely decoupled system. And this is very interesting because we expected that the top patch is like a regular scatterer center. But it's not the case when we plot the current map. So we plot the current map for these values of the low twist angle. Voltage gauge is measured from the sharp neutrality point, and this bias. And you can see that the current is localizes on the AA stacked regions on both layers. So remember that this patch is completely decoupled from the contact. So the current should be completely meshed here in this region, and you can see that is not the case. So they have similar values on top and bottom and top layer, and it's completely localized on the AA stacked region. So probably this is a clue that the top patch is actually responding to the electric field. So probably this is it's a signature of the paramagnetic response of our molecule. So with that, we proceed to calculate the magnetic moment. So we use the regular equation for the magnetic moment. And you can see for both enantiometers, so for positive and negative twist angle. And you can see we put a mirror plane here that one is the mirror image of each other. This is the magnitude of the magnetic moment. So we have a magnetic response for our twisted bilayer graphene. So this is like, we are now sure that we are actually inducing a chiral response of the barrier. And this corresponds with basic transformation, what is expected for an infinite twisted bilayer graphene, because we can, in infinite systems, we can get the negative twist angle. We can go from the positive to the negative, just with a parity transformation and then a mirror transformation. And you can see that's what we see here when we plot the magnetic moment. Now we can check with the components. Here I plot the magnitude of the magnetic moment, but we can see here the magnitude of the magnetic moment. So you can see that negative and positive twist angles, so both the mantiometers are just producing what is expected for a chiral system and follow this transformation. So, okay, we are now sure that we have a chiral response of our system. We obtain this true chirality only for low twist angles and small energies. If we didn't find it for large twist angle. So the twisted bilayer molecule is basically a chiral for low twist angle and low energies. And you can see here the magnetic moment. So this is the global magnetic moment of the device. And you can see here that basically for low energy is an in-plane moment, and then we have an out-of-plane component. And for larger energies, we don't have any magnetic response. So, well, the magnetic moment is originated from circulating current. So we look at the current distribution of our device. And you can see here on the left the actual current. The red current corresponds to the current on the bottom layer, and the blue arrow corresponds to the current on the bottom, on the top layer. So it's a little difficult to interpret these results, as you can see, but you can find a defined pattern. So we try to analyze this in a simplest way, and we define now two currents. So one current that we call magnetic current, and other current that we call the total current. So we want to evaluate the counterflow, because you know that we have a large in-plane magnetic moment, so that only can be produced, but counterflow. That means that the current on the bottom layer are flowing in opposite direction to the current on the top layer. And they, in some region, they should be closing the circuit. So we calculate the magnetic current, and you can see a perfectly defined pattern that follow the transformation expected. And the magnetic and the total current, we see circulating currents on each hexagon. This current is 20 times larger than this one. In principle, in a magnetic system, this should be 0, but we think that it's not 0 because of we are injecting current into the system. Well, now, since we know that we have a magnetic current, we need to double check if this response is due to the stacked regions, is due to the electrons localized on the stacked region, or is simply produced by the localized state on the barrier. You know that localized state can have circulating current. So we decide to test those two approaches. The first one, that is the global approach, that's I already showed, and the other one is the effective or local approach, when we are going to calculate the magnetic moment on each of these stacked regions. So you know that the magnetic current is only defined on the stacked region when we found the counterflow. And we calculate the in-plane magnetic moment, but basically we want to check if the value of the magnetic moment calculated from the global formula is equal to the magnetic moment calculated by the local formula. You can see here, the answer is yes, they have similar values, especially this peak. We calculate, we choose this region with a large value, because as I already mentioned, it's only valid, our local approach is only valid on the stacked regions. And this is a plot of the magnetic current, where we average on the hexagons. And you can see perfectly defined counterflow and perfectly defined magnetic current. And also you can see some source and sinks of the magnetic current. This means that we are seeing here the region where the current is going up and going down. So this is just an image that we have here, a circulating current. We have a current loop on the AA stacked regions. Well, now we have a clear image of the physical process in our device. And initially, I showed for magnetic, the magnetic response for a nanoribbon, for a molecule with armchair edges. So now we want to check if this magnetic response is a general response and it not depends on the edge orientation. So we now change for zigzag nanoribbons. We now inject the current from the bottom edge on the on this edge, the upper and the lower edge, to create a magnetic zigzag twisted bilayer molecule. Note that the top patch remains the same. We can use the same twist angle for both systems. And this is also interesting because you know that current distribution in zigzag and armchair have different patterns. For example, armchair nanoribbons, the current is distributed along the width of the nanoribbon, while armchair nanoribbons, while zigzag nanoribbons, the current runs along the center of the nanoribbon. So we check if we have a magnetic response for this kind of system. And we here, for the same region that I showed you before, we have the magnetic moment, the in-plane magnetic moment calculated by the local and the global formula for the armchair and zigzag orientation. It's actually the same region, but the first time the current is injected from the left to the right, and in the zigzag is injected from the upper to the lower edge. And you can see that they have similar magnetic response. And when we plot the magnetic current, you can see that the magnetic current now is rotated 90 degrees. We have now, for the armchair nanoribbon, where the current is injected from the left to the right, we have the distribution. And here we have so the current was rotated, so that a response to the current, because they changed the magnetic current that is the current that is exciting the magnetic dipole. So well, I reached the end of the presentation, but I want to let you an idea. We found a chiral response. We found magnetic moments, in-plane magnetic moment generated by the localized state. This is a triangular lattice, and the value of the magnetic, we couldn't find saturation, so that means that the orientation is in all the magnetic moments on the AA stacked region are not pointing to the same direction. We have a net magnetic moment, but we are not saturating the system. And the orientation is random. We didn't understand why is the orientation, why there is a preferred orientation. We test if our results are robust, and what we found is that they are robust. We induce a lattice relaxation, that is a very common process in twisted bilayer graphene. We include vacancies and other kind of defects, and we continue finding a magnetic moment. And we also calculated for an infinite system, and we found a magnetic response of the AA stacked regions. So as a conclusion, is actually we found a chiral response of these devices, and well, this is the final.
Okay. Thank you, Dario. Okay, the talk is open for questions. Guilherme?
Hi, Dario. Nice talk. Do you have an answer for why do you find the chiral systems only on small angles?
We believe that is because of the localization of the systems, of the wave function here. So we have for low twist angle, the top and bottom layer are highly coupled. The coupling is really strong. And you are localizing here the wave function is localized on both layers.
Just on the 6 atoms.
Exactly.
around
Probably
the
it's the same effect when you have a localized state in one only bidimensional system, that we have localized state and the current circulating here. Now you have localized it on both lattices, on top layers, and probably that force that the magnetic dipole, the current circulates between the layers.
Okay, thank you.
Because we only find the answer, the magnetic response for low twist angle. That's when the both layers are strongly coupled.
Lydia.
Hey, Dario, very nice talk. Not sure if you mentioned, and I missed it, this effect is also robust if you consider a substrate, for instance.
Sorry.
A substrate, if, for instance, if your bilayers are on top of a substrate, you still...
We consider a relaxation of the lattice.
But not like interaction with the substrate?
No, no interaction with the substrate. We consider relaxation of the lattice.
Okay, thanks.
It's like the common disorder in twisted bilayer graphene relaxation. We don't have perfectly defined AA stacked regions. But the results are robust, changing the localization of the AA stacked regions.
Maurice.
So these small angle configurations, they're actually stable, so they will actually stay.
Yeah.
So if all degrees of freedom are free to relax, they will stay like this and will not rotate back?
No. Okay, what we observe is the magnetic response. We have a smaller magnetic response. The value of the magnetic moment is smaller, but the regions continue to be localized. I can define AA stacked regions, even for the low twist angle.
Alexandre.
So how do your results talk with the appearance of superconductivity on these small angle as well? I mean, how does your results correlate with that?
Okay, with superconductivity and in principle, they don't have nothing to say because we are not considering interaction. But now there is a lot of research on chirality on twisted bilayer graphene and the nematic phase. So basically, we observe an isotropic response. And for example, we have some results I didn't show. This is an work. We are working on that. That is how the anisotropy of the conductance. And there are a lot of works on twisted bilayer graphene studying the nemacity of this twisted bilayer graphene, including interaction.
More questions? So let me try to. I would like to talk to you later on, but usually, so you have in order. If you have graphene, you have your band and the spin up and down are degenerated. So somehow you turn graphene and then you split this degeneracy and then you originate a magnetic moment in this atom.
No,
so it's not, what is the origin of this magnetic moment that is very small, right?
This is per atom. This is per site. No? The magnetic moment, the whole device is the magnetics per atom. But the origin is basically the current lobe between the top and the bottom layer. So this is the origin. We have a magnetic response because we have the current when the both layers are strongly coupled. The top layer reacts to the flow of the current with a paramagnetic response. So the current flows in the opposite direction and creates a current loop. We didn't include the spin or something like that. So this is just how the system reacts when it's like a chiral response. So we put an electric field, and in a chiral system, the electric field induces a magnetic dipole. This is basically the chiral response of the system.
Okay. More questions? Well, if not, let's thank all the speakers and we go for a coffee break. Thank you.
We're back at 4:30, and remember to sign the sheet if you want to go to the dinner.